All right, folks, so this is lesson 10. We're going to continue our work on the dot product. Okay, so last time we defined this new operation called the dot product. We said that if we have two vectors and we want to define a product operation on them, we defined it as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. All right. Now, there was certainly one surprising thing that came out of this definition, I would say, is that when you look at what you get on the side, on the right-hand side, what's special about this object that you get on the right-hand side that might be a little, a little surprising, is that you get a scalar. Okay, so I would agree with you that you'd think the more natural way of defining the product between two vectors is to produce another vector. When we add vectors, we get a vector. When we subtract vectors, when we scalar multiply a vector, we get a vector. Okay, but here we're defining this product and we get a scalar. But again, this is where I want you to keep in mind, what is the point of defining some new operation? Well, presumably it's to accomplish something. It's to get something that's going to be useful to us. All right, so hopefully we can show that this is going to be a useful operation. And the other thing we want is we'd like it to kind of fit in. So we definitely can't have it contradict anything we've seen in the past. And then even better is we'd like to have it fit with what we've done in the past. And we saw that this does fit with multiplication in 1D. Okay, so if you have your number line and you're multiplying two vectors, say that have the same direction, whether they're both positive or both negative, well, the angle between them is equal to 0 in each case, and cos of 0 is equal to 1. So it's just a matter of multiplying the two absolute values. It makes sense. 2 times 3 is 6. Negative 2 times negative 3 is also 6. Whereas if you're multiplying two numbers that are in opposite directions, okay, you want the product to be negative, and here the angle between the two vectors is 180, and cos of 180 is negative 1. So it definitely fits with multiplication in 1D, so that's good. It's not contradicting anything we've seen in the past. Okay, what remains to be seen is what is the usefulness of defining the operation this way. All right, now we saw a couple of things that it had. So we saw that this was commutative. Okay, because in the end, the angle between two vectors doesn't change whether I write u dot v or v dot u. And since these are just numbers, well, numbers are commutative. So we know it's commutative. We saw some other things. What was a particularly interesting angle we looked at that might give some indication as to how this might be useful? Okay. Yeah, 90 degrees. We said, well, wait a minute, when the angle between them is 90 degrees, in other words, when the two vectors are perpendicular, the dot product is 0. Okay, so that's interesting. Okay, now, before we move on, I would say that there's a bit of an issue with this definition that we're giving, because think about where we've been moving and what direction we've been moving in terms of working with vectors. What is sort of very inconvenient about well, in the end, 3D is not that big a deal because we know how to find the magnitudes. We saw yesterday that you can find the angle between the vectors. So what's the problem with all this? And again, problems may be a strong word. I would say maybe inconvenience is a better word. Well, finding the angle between two vectors takes a long time. In fact, we were kind of implying last class that we were trying to find a better way to determine the angle between vectors. So the problem here is not so much 3D, it's that this is not very good when it comes to working with algebraic vectors. It's fine when my vectors are given geometrically, okay, which is why we call this the geometric definition of the dot product. But what we would like is a definition that relies only on working with the individual components. In other words, if I define u to be, say, x1, y1, and v to be x2, y2, can I find an algebraic definition for this dot product? In other words, can I find a way to determine this value by just operating on the individual components? Okay, that's the whole beauty of algebraic vectors, is that you're only operating on the individual components. You're not relying on knowing the magnitudes and knowing the angles. All right, so this is our goal here. Okay, so let's draw a diagram. Okay, so this is where we kind of didn't get to it last time. So let's say I've got, some vector u. Okay, so say this is my x1, y1, and say I've got, some vector v. This is my x2, y2. Okay, I want to find a way to determine a formula for the dot product that only relies on the components. But I need it to be equivalent to this one here. So I'm going to start with that definition. I've got u dot v, I know is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. Is there any issue with determining expressions for these two? Do we know how to determine expressions for these two based on the vectors we have? Yes, no? Yeah. We have a definition for the magnitudes of these vectors. So that's not a problem. All right. Now, what about the angle between them? Do we have a way of determining an angle between them? How did we determine the angle between these vectors? Let's be more specific. We had some options here. What are the options we had for determining the angle between the vectors? Okay, one of them was cosine law. Okay, was to create a third vector using subtraction. And the other one was determining these two angles and then subtracting them from 180. But I'm going to use the cosine law one. Who's going to tell me why I'm going to stick with the cosine law version of it? I don't know that it's necessarily easier, but why am I going to stick with the cosine law version? Who can tell me why it's vitally important? Okay. There you go. Because I'd like something that translates nicely to 3D. Okay, and what we saw last class, at the beginning of last class, was that determining the angle using the cosine law translates perfectly into 3D. Okay, I have any two vectors in 3D, even if these are, out in space somewhere, I can still create a triangle by taking the subtraction and still use the cosine law. Now I'm going to do 2D just because it's going to be less writing, but hopefully you'll see that this works perfectly well in 3D. Okay, so what I'm going to do here is I'm going to create my vector. Okay, this is u minus v. Okay, because I'm going from the tip of the second to the tip of the first, and my vector u minus v. Of course, let me just write it down here. Well, again, I can just work algebraically. It's just x1 minus x2, y1 minus y2. Okay, and all of this you could do in 3D. You just have a z1 minus z2 along for the ride. All right, so let's go ahead and input this here. Well, magnitude of u is just the square root of x1 squared plus y1 squared. Okay. Magnitude of v is just equal to, okay, x2 squared plus y2 squared. Okay. And now here, I need to find the cosine of the angle. But again, let's use the cosine law. So what is the cosine of theta going to be equal to? All right. Well, I just rearrange the cosine law the way I normally would. Okay, so I start with the opposite side squared. So it's just going to be the magnitude of u minus v squared minus the squares of the other two sides. So minus the magnitude of u squared minus the magnitude of v squared. Okay. No problem there. All over -2 times the magnitude of u times the magnitude of v, the side lengths of the other two sides. So now, actually, look at what happens when I now replace cosine theta by this equation. What very nice thing happens here? Can somebody see what very nice algebraic?
The denominator cancels out?
There you go, or at least certainly most of it, because you realize, hey, wait a minute, this is just the magnitude of u. Magnitude of u. I didn't even really need to write that out. There you go, cancels out. Okay, and here, same thing. This is the magnitude of v in the numerator, cancels out with the magnitude of v in the denominator. Okay, so what I'm left with is this expression over -2. Okay, so pretty nice. You know, it's certainly a nice start. So now let's go through the process here. I think we're going to have to, actually, put everything and lay it all out, because remember, I'd like my answer to involve just the components of these two vectors. So let's go here. Now here, notice I have the magnitude of u minus v squared. So square root's already gone. So let's do that here. So what does that leave us with? The first component squared plus the second component squared. So we have x1 minus x2 squared plus y1 minus y2 squared. Okay, normally you'd have a square root, but it's being squared. All right, minus the magnitude of u squared. Okay, so again, this is just going to be, notice here I put brackets to make sure I take into account this subtraction. So this is going to be x1 squared plus y1 squared, and then minus here, this is just going to be x2 squared plus y2 squared, again, because the square root, sorry, that one should have been squared there. I just noticed that little mistake. Okay, all over -2. So at this point here, this is still looking pretty ugly, despite the fact that we canceled out those expressions, still not looking great. So let's hope this looks a little better. So we're going to have to expand these out. So x1 squared minus 2x1 x2 plus x2 squared. So I'm just, expanding these binomials, okay, plus y1 squared minus 2y1 y2. And maybe even at this point, you can start to see what very nice thing is going to happen at some point. Okay, let's distribute my subtraction. So minus x1 squared minus y1 squared. Same thing here, minus x2 squared minus y2 squared, all over -2. All right, and this is where I'm hoping you're seeing all the beautiful things that are going to happen here, because the x1 squareds cancel out, the x2 squareds cancel out, the y1 squareds, the y2 squareds. In fact, all the squared terms just cancel out. And so what are we left with here? -2 x1 x2. And somewhere here, there we go, minus 2 y1 y2 all over -2. And that simplifies even more nicely than that, because what do we have? We have x1, when we divide numerator by -2, x1 x2 plus y1 y2. And look at how simple this ended up becoming. From this big ugly expression, would have looked even worse if I had replaced all these things by x1s and x2s, reduces to something very nice, and just about as nicely as one would expect, or would hope. Not necessarily expect, but certainly what one would hope. So one thing I notice here, that this gives me a scalar quantity, all right? And this does not depend on knowing the magnitude or the angle. The only thing it depends on is operating on the individual components, which is exactly what we want when we have a a definition for an operation using algebraic vectors. All right, so our conclusion here is that you have your two definitions of this operation called the dot product. You have the geometric definition, and you now have the algebraic definition. And you can imagine here in this whole process, pretty much everything would have looked exactly the same had I been working in 3D. The only difference is I would have had here Z components all over the place, but the same thing would have happened. The Z squareds would have canceled out, and the only thing I would have been left over with here would have been a minus 2 Z1, Z2. So this same definition applies in 3D. It would just be x1, x2 plus y1, y2 plus z1, z2. Okay? Only depending on the individual components of the vectors. All right? Now, what this means is that finding this dot product is very easy using algebraic vectors, and I'll give you a little bit of a tip for what we're going to be doing later on. Very often the usefulness of the dot product is when you combine, oh, my thing got stuck there, is when you combine the two definitions together. Because if u dot v is equal to this thing and it's also equal to that expression, it means that these two expressions are always equal. So I want you to keep that in mind. But before we take a look at some applications of this dot product, so we can finally see that yes, there is a usefulness to defining the product in this way, we're going to take a look at some properties, because as we already saw, we know that dot product is commutative. What other properties might it have? So what we have here, I'll just go to the oh, looks like I accidentally shut it off. Let me just open it up here. Okay. Okay, we're going to take a look at these two properties. All right. So this property here basically says that you can take the dot product and then multiply it by a scalar, or you can first multiply the vector by a scalar and then take the dot product. It shouldn't make a difference. So this is an associative property. Doesn't matter what order you do any of these multiplications. And this one, well, this is really, the one we're probably going to use most often, is a distributive property. Okay, we would hope that this is distributive under dot product and vector addition. Okay, because again, we want this to have the same properties as regular multiplication in one dimension when we're just working with real numbers. Okay, so can you distribute the dot product to a sum of two vectors? Okay. All right, folks, so we're back. So let's take a look at this first one and see how we could set up a proof like this. Okay, so you'll notice that the first thing I do here is I define what I'm going to use. So in this case, they're asking me to do this in 3D. So I define two random 3D vectors, and k could be any scalar. Okay. And the first thing I do is I just replace, I'm going to start with my left-hand side, and I just replace these two vectors by their 3D representations. And this is where now I just start to apply my properties. Okay, so I've got this big bracket here. I'm going to have to do that first. So the first thing I do is I apply the dot product definition to these two vectors. Okay, but now at this point, everything that I have is just a bunch of numbers. So I can now apply my knowledge of distributivity for numbers. Okay, so by the way, folks, stop me if you need any elaboration here. So now I'm just going to, multiply everything out. So I just distribute k to each of the components. And now this is where, sometimes we used to do with identities, with trig identities, is I sometimes look to the other side for a bit of inspiration. So it looks as though I want to combine together this k and this vector u. So that's what I do here. This is a perfectly legal operation with real numbers, is I can group together the multiplication of k times x1, k times y1, k times z1. Okay, but now look at this here. I go backwards on the definition of the dot product. I realize that the way I've written this expression out can be rewritten as a dot product. Because remember, dot product is the first times the first, second times the second, third times the third. So this is a perfectly legal operation. But then what can I do here? I can take out, again, I can go backwards and take out that scalar multiple and write this first vector as k times x1, y1, z1. And lo and behold, I have exactly what I wanted to show. That I can first multiply u by the scalar multiple k, and then take the dot product with v. It's the equivalent to taking the dot product and then multiplying by the scalar. Okay? And what we're going to see is, this might not look like an important property, but we'll see in a second why, or at least in a little bit, why this is actually very useful. It's going to make our life much easier when I'm operating with the dot product. Okay, here I'm going to do something very similar, except now I'm working with 3 vectors, and in this case here in 2D. So I do the same thing. I'm going to start with the right-hand side. I'm just going to rewrite this, with the left-hand side. I'm just going to rewrite this left-hand side, but with the vectors in their algebraic form. Here I do my bracket first. I start by adding those 2 vectors. Now I've got the dot product of 2 vectors. I apply my formula for dot product. Here again, this is now a whole bunch of numbers, so I can use the distributivity of real numbers, and I just distribute. Okay, but now let me again look to the right-hand side for some inspiration, and I realize what I want to do is I want to group together expressions with u and v and expressions with u and w. So all I'm going to do is I'm going to use my commutativity of addition to move things around. So I put all the things with 1 and 2 together and those with 1 and 3 together. So u and v, u and w. So I just move things around. I essentially just move those using commutativity, and I group together all the expressions with u and v and those with u and w. And then I realize, hey, what is this equal to? That's just equal to u dot v, and this is equal to u dot w. And look what I've just shown. I've shown that dot product is distributive. So when we look at all these characteristics, essentially the lesson here is that I can work with vector expressions in the same way that I work with algebraic expressions, at least when it comes to scalar multiplication, dot product, addition, subtraction. So all those tools we have for doing algebra with algebraic expressions, we can now just apply them. So things like distribution, okay? Maybe, as we'll see later on, taking the dot product when it's 2 pairs of sums, okay? So let's now take a look at one of the big uses for the dot product, okay? This is certainly not the only thing that it's useful for, but it's certainly a biggie, all right? Is at the very beginning of the last lesson, the first thing we realized was that determining the angle between 2 vectors in 2D and especially in 3D was not an easy process, okay? But my claim is that now if I have 2 vectors in 3D, I can use the dot product to determine the angle between these vectors without having to set up a triangle, without having to subtract the vectors, without having to use the cosine law. I am claiming that I can use the dot product. All right. And this is because now these vectors, determining these magnitudes, fairly easy to do, a bit of work, but fairly easy to do. But now I have an algebraic way for easily determining the dot product. So in the end, the only thing that's left in my equation that's not easy to do is the angle. In other words, I can solve for the angle. All right, and this is one of our first really important uses, is that if we need to determine the angle between 2D or especially 3D vectors, it's as easy as determining the dot product algebraically, which is quick, determining the magnitudes, which is also quick, and just solving for the angle theta. All right, so this is what you're gonna attempt to work on now. So let's take a look at these two examples. So I give you an example in 2D where I want you to find the angle between the vectors, okay, but without that whole long process that we looked at last time. And same thing with 3D, is make use now of this beautiful new definition of the dot product to determine the angles between the vectors, okay? So this is what I was talking about before, how often the dot product is useful when you're combining the algebraic and the geometric definitions. All right. All right, so we're back. Let's take a look at these examples here, and we'll take a look at them at the same time because it involves the exact same procedure. Okay, so in both cases here, the goal is to use the dot product and use the fact that the dot product is easy to determine algebraically, and these magnitudes are relatively easy to determine. Okay, so you'll see on the left-hand side, what I apply is the dot product definition for algebraic vectors here in 2D, here in 3D. And then it's just a matter of finding the magnitudes of those vectors. And lo and behold, the only thing that's left over is the angle. And so from there, I just do a little bit of algebra, and I'm able to determine approximations for these vectors, or the angles between the vectors. All right. Now, if you were to draw this out, 4, 3 would be, somewhere there, and negative 6, 1 would be somewhere on the other side. Not surprising. You can easily see that it makes sense that this should be an obtuse angle. In 3D, you don't even want to have to think about that. So one of the things you're going to have to rely on is that your diagrams in 3D aren't necessarily going to be accurate, okay? But you're going to rely on your trust and your faith in the operations that we've defined, and this is why we prove them, to make sure we have complete faith that these work, okay? So this would be the angle between the two vectors in 3D, all right? Any questions on this here? Okay, so this is definitely one of the big uses, at least initially, for the dot product, is that it allows us to easily determine the angles between algebraic vectors. Now, I don't think this should be surprising because remember how we came up with this algebraic definition. It was by using the angle between the vectors. All right. So this one here now, okay, that sort of implied that another important aspect of the dot product is that it helps us when dealing with perpendicular vectors, which is something we're often doing, and we're going to see how, again, this is going to be extremely useful for us as time goes on. So what they tell us here is they tell us that these two vectors are perpendicular to each other, and they want us to use that information to determine the value of x, okay? So I want you to set up an equation and try to solve it. This here really should not take too much time, so I'll leave you just a couple of minutes. All right, so let's take a look at number 4 here. So What should have been the first thing that I write down? Who could tell me the first thing that I should have been writing down to solve this problem? Okay, and again, great to hear from people who maybe don't speak too often. Okay, so we essentially take the fact that they're perpendicular, and we know that this means that the dot product is equal to 0. So that's going to be my first step, is the dot product is equal to 0, and then from there I can just determine the dot product using my algebraic definition, and I end up with an equation, and in fact a fairly simple quadratic equation. So it actually turned out that there were two values of x that I could use to make these two vectors perpendicular to each other. All right. So we've got a couple of more problems here on the sheet. We'll get to one of them for sure, and there's certainly a similarity to both of them. All right. So let's take a look at these here. And it says if the angle between U and V is 60 degrees, and right away, what's the first thing we need to notice here? What should the light bulb should be going on? Because there's a piece of information here. Exactly, we've got the good old hat, which means that, whoops, sorry about that, which means that these vectors have magnitude 1. So that's known. So notice here, they're giving us a lot of geometric information. They're giving us the magnitudes of the vectors. They're giving us the angle between them. But I suspect that when you're starting off this problem, you're going to be working a little more algebraically. Okay, so could you do 6u, take my vector u, which has magnitude of 1, take 6 times, and then add vector v, knowing the angle between them? Yes, you can. Can you subtract u minus 2 times v? Because you know this is magnitude 1, magnitude 2 with the angle between them. So you certainly can solve this problem by independently determining this addition and that subtraction, and then taking the dot product and working completely geometrically. I am going to strongly suggest that you do not do that, okay? Because you can imagine that's going to be a very long process, probably take more than the 15 minutes we have left in this lesson, okay? So what I want you to do is I want you to use the fact that we determined all those characteristics about the dot product, in particular, that it's distributive, okay? And because it's distributive, it means that you can simplify this expression, which is the dot product of two sums, or sum and difference. Difference is just like a sum, okay? And you can essentially distribute this the same way that you could distribute two binomials. Now, once you do the distribution, you should notice that some of those terms are going to be very nice terms, but there will be some work left to do. So what I want you to do is start this problem off. I won't give you too much time, but I want you to at least start it off, all right? And see how far you can get. Okay, so we're back on this one here. So let's take a look at what we do. So notice here, what I suggested is that you don't go ahead and use the geometric properties right away, but to simplify first, okay? So I'm using the fact that this is distributive, okay? So what I do is I do 6u dot u, my firsts, okay? And then I keep going, 6u dot negative 2v. Now remember, the order in which I do these from that first property we proved doesn't matter. So that allows me to write it as negative 12 u dot v. Here we've got plus v dot u, and then minus 2 v dot v. Okay. Now, what do you notice about these two? What happens when we dot a vector with itself? Does anybody remember what we determined last time? What is the result of dotting a vector with itself? Well, think about it. It's magnitude of u times magnitude of u times cosine of the angle between them. Angle between them is 0. Cos of 0 is 1. So this is just equal to 6 times the magnitude squared. Exactly. Okay. Here, notice that u dot v and v dot u are commutative, meaning they're equal. So I can just bring this together and write it as negative 11u dot v, and similarly here, okay? But of course, we also have that the magnitude of those vectors are equal to 1. So I just have 6 minus 2 is 4. And now this is where I have to use the geometric properties, because I'm still left with a u dot v, but luckily I have enough information to calculate, oh, I want to hide that, to calculate u dot v, because it's just, now I'm going to apply the geometric definition instead of an algebraic one, and I know the two magnitudes, and they've given me the angle between them. They've given it to me directly, okay? And so in the end, I'm able to determine the value here, all right? So what we see here is this combination of using algebraic properties to help us simplify, and then using the geometric properties in order to be able to calculate, okay? So very typical type of question. Now, since it looks like we've got enough time here, we have about 7 minutes left, it looks like we do have time to work on this last question, okay? And this is in some ways very similar, I hope you can see, to the one above, but notice the information they give you. You know, this question was very nice because they outright not just gave us the magnitudes of the vectors, but they gave us the angle between them directly. You notice here, no such luck on that one there, okay? So I'm going to give you some time to work on this. It's going to be very similar in terms of the setup, but how you actually use the geometric information is going to be a little different. So I'll give you a bit of a hint here. You really should be planning on drawing a diagram to help you solve this question, okay? So it's 54. We'll give you to like 50, maybe we'll give you 3 minutes to solve this, to 57, and then we'll have just enough time to take it up, and that'll be the end of today's lesson. All right, so we'll be back in a little bit. All right, so we're back here. So let's take a look. I've got it up here. So it's a little small. Well, hopefully you can see that here. So the first thing I do is I do exactly what I did before, is I just multiply it out as though I was multiplying two algebraic expressions. Okay, so essentially I FOIL it, if you use that term, and in the end I simplify. Now at this point here, you know, I kind of know that u dot u is just the magnitude squared, which is just, since magnitude of u is 1, so I know that's just going to be 6, and same thing here, I know v dot v is the magnitude of v squared, since the magnitude is 1, just minus 5, so nice and easy. And I know that u dot v is equal to v dot u because of the commutativity. So I'm able to simplify a little quicker than I was before. Okay, so I end up with this expression. But now I have to calculate u dot v. I know the two magnitudes, but I do not know the angle between them. So this is where I have to really go and do something geometric, and I actually have to use the fact that I know the sum. So what did I do here? I place my two vectors, u and v. They each have a magnitude of 1, and I place them tip to tail so that I can add them together. And what information did they give us? They gave us that the sum has a magnitude of √3. And now all of a sudden I've got a triangle where I know all three sides, and so I can calculate this angle here using the cosine law, okay, which I do here, okay. But what's very important with respect to this angle of 120 that I just found? Why is that not going to be the angle that I put into my equation? Who's going to remind us why this is not the angle to use? Okay, exactly, because this angle theta is the angle between the vectors. Okay, that's not what we found here. The angle between the vectors is supplementary to 120, so equal to 60. So that's why I put that in there. So you see here how, again, I really had to use this combination of my algebraic knowledge in order to simplify the expression, but then I still had to use my knowledge of the geometric aspect of vectors in order to calculate the angle between them. Okay, so kind of a combination of everything. Okay, so just to let you know that so that's the end of the lesson. Just to let you know that next week's quiz, okay, because you folks are going to be a little ahead, is actually going to end essentially at this question here. Okay, the last thing that you'll be using is the fact that perpendicular vectors have a dot product of 0, finding the angles. So this is where next week's quiz is going to go till. Of course,